Hello everyone. Today we are going to cover section 4.2, which is the final section of our three existence theorems. And this one's on the mean value theorem. So we've had two existence theorems already. The first one was the intermediate value theorem, which said if a function is continuous and we know a value at one endpoint of the interval and a value at the other endpoint of the interval, our function has to hit every value in between those two. So a lot of times we would use it to say, hey, this function can have a 0 on this interval, or this function could equal -2 on this interval. It's an existence theorem. It tells us that something happens. Our second existence theorem was the extreme value theorem, which we did at the very beginning of chapter 4, which said if I have a function that's continuous on a closed and bounded interval, that function has an absolute maximum value and an absolute minimum value. Again, told us that it exists. Our third theorem is the mean value theorem. So to illustrate what it talks about, I thought I'd show you this example. We go through this. So let's say you're driving on the tollway and on the tri-state, and you go through the O'Hare toll booth at 55 miles per hour at noon. And then you hit the next toll booth, which is the Cermak toll booth at 12:09. You're also going 55 miles per hour. Then a couple weeks later in the mail, you get a ticket from the state of Illinois that said you were speeding at this date and time. And you think back and you're like, no, I went through those toll booths at 55 miles per hour. I was not speeding. Well, mathematically, they can prove that you were speeding. Because if you were going between those two toll booths, which are 12 miles apart, and it took you 9 minutes to get there, if we think of just the old equation from Algebra 1, distance equals rate times time, and you know the distance is 12 miles, and the time is 9/60ths of an hour, you're going to get 80 miles per hour is your average speed over that time. So even though you went through one toll booth at 55 and the other toll booth at 55, you averaged 80 miles per hour. And what the mean value theorem says is that since speed is continuous and differentiable, we can take the derivative of it at every point. If your average speed was 80 miles per hour, you had to have a point where your speedometer said exactly 80 miles per hour. And so you could get a ticket for speeding. Now, this has actually been discussed in the past as a way that they could quickly raise revenue in the state of Illinois, but I don't think it would ever go through and pass. It'd be scary if it would, because many of us would have speeding tickets, multiple speeding tickets for our way around the tri-state. So this is the mean value theorem. So let me kind of talk about it mathematically, show it graphically, and then we're going to do two examples to show you algebraically how we use it. Anytime we do examples in these videos, I know we haven't done a lot of videos so far, I encourage you to, once I put the example up, you pause the video, try it, then unpause it and see how you did. So the mean value theorem, which we abbreviate most of the time as the MVT, goes along with the IVT and the EVT. And so hypothesis. So what's the beginning? What needs to happen? So let's say we have a function. If f of x is continuous on the closed interval a to b and differentiable on the open interval ab, then what can we conclude? Here's our conclusion. Then there exists a value c. See that idea of an existence theorem. There exists a value c on that interval a to b such that, and here we're going to say, remember what we've talked about the toll booth. It's somewhere where the average rate of change, if it's 80 miles per hour, there has to be a moment where my instantaneous rate of change equals 80 miles per hour. So there's got to be a moment where my instantaneous rate of change is equal to the average rate of change. So unlike our other existence theorems, this gives us a tool to find out where that value is. What is that value where my instantaneous rate of change, which is represented by the derivative, is equal to my average rate of change, represented by our formula for slope. So if we think about this geometrically, what's going on here? Well, let's say I have a function that's f of x. It's smooth and continuous, so since it's smooth like that, we know it's also differentiable. Here's a, here's b, here's f of a, and f of b would be up here. So if we think about the average rate of change between 2 points is the slope of this secant line that goes between those 2 points. And so the question is, can we find a tangent line that has that exact same slope? Well, I think we pretty clearly can see if we follow this along, I think we probably have one about right there. So that would be my first value of c. And as I go around, it looks like I probably have a second one right here, my second value of c. So there can be multiple values of c. So in terms of velocity, things like that, it's when the instantaneous velocity equals the average velocity. In terms of geometrically, it's when the slope of the secant line is equal to the slope of the tangent line. That's what we're looking for with the mean value theorem. So let's see an example here and how we can solve it using algebra. So I'm going to read through it, and what I would suggest doing is pausing the video, trying the problem, and then I'm going to go through a very structured way of how to approach the mean value theorem problems. Find all values of c that satisfy the mean value theorem for f of x equals 2x squared plus 1 on the interval -1 to 4. So go ahead and try the problem. Okay, so let me show you how I'll organize the work so we can see the solution. So the conclusion, the mean value theorem, is f prime of c equals f of b minus f of a over b minus a. For us to be able to use this, our function has to be continuous and differentiable. Well, our function's a quadratic, which is continuous. Its derivative would be linear, which is also continuous, so therefore f of x is also differentiable. So I'm going to start with, well, let's just find f prime of c. So f of x is 2x squared plus 1. That means f prime of x is 4x, and f prime of c would just be 4c. Okay, derivatives aren't going to be difficult in these problems, not at all. Now, let's take care of the average, the f of b minus f of a over b minus a. And so on my interval, my first value is going to be a, my second value is going to be b. So I have f of 4 minus f of -1 over 5 minus -1. Now f of 4 is 33. F of -1 is 3 over 6. So I get an average rate of change. Oh, sorry, this should be this is a 4, not a 5. And so this is a 5 here. And the average rate of change then is 6. And so now all we have to do is find, well, what value of c makes the instantaneous equal to average. And that point is going to be when c is 1.5, or the x value is 1.5. Now, if you didn't use c, if you just did f prime of x equals 6, so 4x equals 6 and x equals 3/2, they're not going to mark it wrong. It's just the idea of you want to have a different variable to represent a value on the domain, so that's why they're using c. So that's how you apply the mean value theorem. Pretty straightforward. All right, why don't you try example 2? Example 2, same directions. Use the MVT to find the value of c that satisfies it, where f of x is x cubed minus x squared minus 2x on the interval -1 to 1. So again, pause the video, try the problem, then unpause and check your solution and see how you did. Okay, I'm going to go through the problem exactly like I did the last one. So if f of x is x cubed minus x squared minus 2x, our derivative just uses the power rule, so 3x squared minus 2x minus 2, and then f prime of c just means I'm replacing the x with the c. All right, average rate of change, the f of b minus f of a, really just finding the slope between the endpoints. So for this one, we would have f of 1 minus f of negative 1 over 1 minus negative 1. F of 1 is negative 2. F of negative 1 is 0 over 2. So I think we get negative 1 for the average rate of change. And now we're going to go ahead and just set the instantaneous rate of change equal to that average rate of change. And if I do that, we get a quadratic which is factorable, I believe. So let's see, we have 3c and c minus 1 plus 1. So we get c to be negative 1/3 and c to be 1. But this value, that's one of our endpoints. And so we're not going to include that on our solution set. It's only going to be the values in between. So in this case, there's one value where this works. So some things to consider when you're doing these problems is these conditions guarantee that it's going to happen, but just because the conditions are not met, the mean value theorem can still be true. So for example, let me just show you a graph. Let's say I have a graph that looks something like, let's say here's A and here's B. And let's say I have a picture that looks like this. And let's say we have that. So if I have this, this is f of A and f of B are the same, right? My secant line is horizontal. Well, I can find a tangent line right here, right? Where it's going to be horizontal at that max. So even though the conditions weren't met, the mean value theorem could still work. What the conditions being met really means is you're going to guarantee that it works. You can guarantee that it happens. And this is an example without, imagine this was continuous and not discontinuous like you see here. That's a specific case of mean value theorem called Rolle's theorem, where if f of A and f of B are the same, then the average rate of change is 0, which means that that tangent line is going to be at a maximum or minimum. So it's just a very specific case of Rolle's theorem. So mean value theorem, you're looking at when does the average and instantaneous rate of change, when are they the same on a function when you have a certain domain window that you're looking at. If you have questions, I'll be happy to answer them next time I see you in class. Take care, everyone. Bye.